going to be doing is testing a claim, seeing if a claim is true or not, finding evidence for or against a claim. Now, by definition, what a significance test is a procedure that uses observations, something that's observed, maybe in some kind of sample, observed data to decide between two competing claims. Those two competing claims are called hypotheses, and I'm going to show you today how to write hypotheses. So there will be two hypotheses for each question. These claims are usually statements about a parameter. Just like chapter 8, your little pink sheet had a whole dotted box about P, which is the population proportion, and then a whole separate dotted box with formulas for population mean. That's exactly how this chapter will be split up as well. We're going to talk about things dealing with population proportion, and then the latter half of the chapter will be population mean, or mu. Okay? First thing we're going to do is this little activity that's going to illustrate the reasoning of a significance test. So when I tell you to, you're going to come back here and you're going to grab a little spinner. It's just a paper clip, okay? And what you have on your paper is this spinner here. And I'll show you how to use that paper clip in just a minute. Let's read what we're supposed to do, what claim has been made, and what we're going to try to do to try to prove that false, true or false. In this activity, you and your classmates will perform a simulation to test a claim about a population proportion. So this is all about P, population proportion. A basketball player claims to make 80% of the free throws that he attempts. That's the claim he's making, that he's an 80% free throw shooter. That is, he claims this right here. So these are the math symbols that he would write for his claim. The proportion of all of my free throws, the population of all of my free throws is 80% if I shoot a whole bunch of free throws. We suspect that he's exaggerating, so we think that the percentage of, in the long run, if he shoots a whole bunch of free throws, we suspect that he shoots what? What is that symbol right there? Less than 80%. I want you to make a note. We think he makes less than 80%. We've got what he's claiming, and then we've got what we think is true. Eventually you'll see that that is going to form two hypotheses, his hypothesis and ours. Suppose the player says, you're standing in the gym with him and you're like, all right, dude, prove it. And he shoots 50 free throws right there in front of you, and he makes 32 of them. So we are observing this happening. Well, unfortunately for him, in that sample of 50 free throws, he only makes 32. P hat, the sample proportion of free throws that he makes is only 64%. That's how you would read that. The sample proportion of free throws was only 64%. Why can we not say right then and there, haha, you just proved it, you're not an 80% shooter because I stood here and watched you and you only made 64%. Why is that not enough evidence that he's lying or exaggerating? Because it's really a small sample size. When we talk about statistics, we can't base things on one little sample. So what we're about to do with the spinner activity is we're going to simulate so that he doesn't have to sit there and shoot 50 free throws over and over and over and over again. We're going to simulate that with this spinner. Is it plausible that an 80% shooter will have a poor performance by chance alone? Look, maybe it was a bad day for him. Maybe the ball was underinflated. Maybe he didn't feel well. I don't know. There are lots of reasons that he could have made only 64% of those shots right in front of you. So what you have on your paper is this little spinner. It kind of looks like a pie chart. And I've split it up. 80% of that pie chart represents making a free throw. Because he claims to be an 80% shooter, that's what this spinner represents. 20% of this is you miss the shot. So what you'll do in just a second when I say go ahead and grab a spinner is you're going to put your pencil in the middle of the little pie chart to just kind of flick the paper clip around like this, okay? And you are going to do this 50 times because we are simulating 50 shots. It really doesn't take that long, so don't moan and groan. Go ahead and make a little T-chart of made and missed because you're going to write tally marks as you go to make this go by really, really fast. So I'll just do a couple to show you, okay? I'm going to flick it. I land on missed. Put a tally mark there. And then I'm going to flick it. I land on made. Make a tally mark. And you can go through and you can do this really fast. If you happen to land exactly on a line, you make the decision of where you want it to go. Very rarely will that happen, but it's up to you to decide that. You're going to do this until you have 50 tally marks. Listen to what I'm telling you now. Then what you are going to do is however many shots you made, you're going to put that here on top of this fraction. You're going to divide by 50 because you're finding the proportion or decimal value of the shots that you made in your simulation. Tell yourself now, decimal goes here. Because guess what? I'm going to go around the room and ask every single one of you in here to tell me your decimal value. So there is no hiding today. When I call you, be ready to give me your decimal because what we're going to do is as a class, we're going to make a dot plot of all of these simulations of the 50 free throws that are being made and the proportion of baskets that are being made, okay? Does anybody have any questions about this little activity? And it shouldn't take us very long. I'm going to do my 50 at the same time you are so that I can kind of gauge how much time you need. Are you ready to go?
Sure.
Okay, ready, go. So once you have your tally marks, you've got the number that you made out of 50, and you've got your decimal value.
Did you cheat on us?
Did I cheat?
Yeah, that's what we got.
No. Yeah, cool. That's fine. It's allowed to happen. So we're going to make this class dot plot. Here's what I suggest before we go around the room and people say their numbers out loud. It will probably be easier for you, at least it was for me in my old eyes, to go ahead and let yourself know like that middle mark is 0.55, 0.65, 0.75. This will just kind of help it go by a little bit faster so you're not having to count each little tick mark. That's just my suggestion to you. I want everybody to go ahead and put my decimal value that I got on your dot plot. So, because this is a small class, we want as much data as we can get. So go ahead and put a dot on 0.72. What we'll do is we'll start with Aiden. I'm not going to call everybody's name, so just pay attention. We're going to sweep this way. So when the person before you goes, then you just say your next one out loud. We'll sweep this way, we'll jump across the room to Ashton, and then go towards the television. All right? No pressure. Just give me a quick little number. All right. Let me zoom out just a tad. Okay, Aiden.
I got 0.74.
0.74. Okay? 8.6. Okay? I don't care who goes next. Mason or Jacob. 0.68.
I got 0.84.
4. Okay?
0.72.
0.72.
Cool.
0.66.
0.84.
8.4. Coming at you, Ashton.
0.78. 0.74.
0.76.
0.66.
Okay, hang on just a second. 0.66.
0.86.
0.84.
0.71.
0.7 what? 0.78, okay. All right. 0.68. 6.5. Okay. 0.62. And here's our class dot plot. This is a sampling distribution of the proportion of shots made out of 50. We didn't just make this for nothing. We're going to reference this in just a second. I want you to turn the page. So back to this whole, the player claims to be an 80% shooter, and then standing right in front of us, he only makes 64% of his shots. Okay? There are two possible explanations for why he only made 64% of his shots. There are only two possible explanations. Either what he's saying is true, he really is an 80% shooter, but he kind of just had a bad day and that just happened by chance alone. Maybe that's one of the things that happened. So he really is telling the truth, and what happened just happened by chance alone. Or his claim is false. He really shoots less than 80%. It's got to be one or the other. Either what he's saying is true or it's not. Those are kind of where we're going as far as hypotheses. One of those two claims, one of those two hypotheses has to be true. Now, if we want to prove him wrong, then we need, this is going to show up a ton in this chapter, every single lesson in this chapter, as a matter of fact. We need what's called convincing evidence that his claim is false. We have some evidence. I mean, he shot 64% right in front of us. That's some evidence that he's not an 80% shooter, but we need convincing evidence. And so we have to base this on many, many repetitions. That's why we did the little spinner activity. And so what I want you to do, it says use your class dot plot, which by the way, second period, your dot plot is completely different from all the other classes' dot plots, as it should be. Use your class dot plot to see how unusual it is that he would make only 64% of his shots. So here's what I want you to do. You are going to circle all the dots that are 64% or lower. 0.64 or lower. Circle them. And how many are we circling? How many of our dots in this class, how many of our simulations resulted in 64% or lower? Only one. Out of how many, though? How many dots total? 1 out of 19. We got a little class here, so that's how you find a proportion. You don't just tell me, oh, I circled one dot. You're telling me one time out of 19 did that happen. And 1 divided by 19 on the calculator is like 0.053 if we're rounding, or 5.3% of the time. You've got to really be easily be able to go between decimal to percentage and back to decimal in this chapter. Okay. That's really a low percentage of time, right? Like, I'm starting to think that this guy really isn't telling the truth and that he is bragging or exaggerating, because he did so poorly, and that only happened 5.3% of the time when we simulated it a whole bunch of times. So I'm thinking there might be convincing evidence that he's not telling the truth. Well, we may come back to that in just a second. I want to talk to you about hypotheses. It's so very important that you understand this whole hypothesis thing, okay? There are going to be 2 hypotheses in each significance test. I've already told you that. The claim that we are weighing evidence against, that's how we word it. We're trying to find evidence against, just kind of like we're trying to find evidence against this guy saying he's an 80% shooter. That's called the null, N-U-L-L, hypothesis. And the symbol for null hypothesis is a capital H with a little sub 0. H sub 0. Yes, it says ho. And everybody thinks it's funny. Okay? That's a null hypothesis. 0 is technically the symbol for null. Now, in our case, the null hypothesis, again, the one that we're trying to find evidence against, is his claim that he's an 80% shooter, that he actually makes exactly 80% of his free throws. Okay, the claim we're trying to find evidence for, remember we had kind of a sneaking suspicion that he was exaggerating, and we're trying to find evidence of that, right? And that's called the alternative hypothesis. Alternative. And it's abbreviated with an H sub A. Looks like a hot. In this case, we're trying to find evidence for what we think, which is that he shoots less than 80% of his, or he makes less than 80% of his free throws. Before we move on, I want to tell you something very, 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 very important that will make life a lot easier for you in this chapter, and that is this right here. See that equal sign? There will always be an equal sign when you write a null hypothesis. Always an equal sign in the HO, in the null hypothesis. It will never be a greater than symbol. It will never be a less than symbol. It will never be anything other than an equal sign in the null hypothesis. So, I'm telling you that on your homework you'll have like a multiple choice question. If any of the multiple choice answers have HO colon and then P and there's not an equal sign there, mark them off. They're not correct. Period. Now, your alternative can have a less than or greater than and even something different than that, which we'll talk about in just a second. Okay, in our example, the alternative hypothesis is called it's called one-sided, excuse me. One-sided. Now here's where I can lose some people, so pay really close attention. What I'm telling you is not super difficult, but you have to just understand like the little ins and outs of it. So it's called one-sided because of the symbol less than. Listen really closely. I think this guy makes specifically less than 80%. I only think he lands on one side of that 80%. I think he lands below it. One-sided. If we were to suspect that he just shot something different than 80%, like, hey, I don't think he's an 80% shooter, but I don't know if he's worse or better than that, I just think it's something different than, that's called a two-sided alternative hypothesis. And I'll show you what symbol you would use for that. So if your alternative hypothesis says less than, or if it says greater than, then it's one-sided because you're clearly stating that you believe the answer is on one side or the other. In this little gray box down here, I'm going to tell you what symbol you would use if it's two-sided. So let's make a quick little note. The alternative hypothesis, the HA, is one-sided. If you're reading along in a paragraph and it clearly states greater than or less than, then you're going to use one of those two symbols in your alternative hypothesis. If you're reading along in your paragraph and it doesn't clearly state less than or greater than, but it says like, I just want to know if it's true, then you're going to use this symbol right here. Not equal to. This literally means different than. It means different than. It means, I don't know if it's lower than or higher than, but it's definitely not that. That's the symbol you'll use for a two-sided alternative hypothesis. When you turn the page, we'll actually get to look at some problems and see what all of this means. Some of you will learn better by looking at an example. It says, for each of the following settings, state the hypotheses and define the parameter of interest. So we need to state the hypotheses, and I'm thinking of the project at the end of this unit. I'm going to have you do this. You need to be able to state them correctly, and you also need to be able to define the parameter of interest, which sounds really scary, but you'll see how easy it is in just a second. Look at Part A. It says, on its website for the 2020 census, The Census Bureau estimates that completing the questionnaire will take 10 minutes on average. That word is really, really important for this problem. We suspect that the time it takes to complete the form may be longer than advertised. So they say, hey, fill out this little questionnaire. It'll only take you 10 minutes. And we think, it's probably going to take longer than 10 minutes. Okay? That word that I circle is crucial because at this moment, you should be able to tell me which we're talking about. Are we talking about a population proportion or are we talking about a population mean? Mean, average, mean. That means in my alternative, in both of my hypotheses, that symbol is going to show up. So there's going to be a mu in my hypotheses. Go ahead and set yourself up with your null hypothesis, H sub 0 colon, and underneath that, your alternative hypothesis, H sub A colon. You'll always put them in that order. Your null goes first. Here's what I know so far. I'm talking about a population average. So I'm talking about mu. So both of my hypotheses will have mu in them. I also learned on the previous page that the null will always have an equal sign in it. Now, what the Census Bureau is claiming is that on average, it takes you exactly 10 minutes to complete this questionnaire. And that's why the number 10 goes there. We're talking about the average, the mean time it takes to fill out this questionnaire. Well, if I think that it's going to be longer than 10 minutes, what symbol would I put? Greater than 10, less than 10, or not equal to 10? Greater than. I think it's going to be greater than 10 minutes. Is that a one-sided or two-sided alternative hypothesis? It's one-sided. Amazing, because if you're just a memorizer, it's because it's a less than or greater than symbol. If you're truly understanding what's going on, is because I think that the amount of time that's going to take is on one side of that 10 minutes, specifically longer than 10 minutes. Okay, the only other thing we need to do is this whole define the parameter of interest. You need to tell me what mu means. You've got that mu symbol in your hypotheses. Well, tell me what it means. And it represents the mean time it takes to fill out or complete the questionnaire or the form. I'm just going to put form, feeling kind of lazy. So tell me what the symbol means. Tell me what it represents in your hypotheses. That's all you have to do in this problem. Now let's do part B. Completely different question here. I get to show you now what a two-sided alternative hypothesis, how it would be worded in a paragraph. According to the National Sleep Foundation, 85% of teens are getting too little sleep on school nights. Percent tells me right away, is this talking about proportion or mean? Proportion, percents, decimals, proportions. So I know that my hypotheses are going to have a P in them, not a mu. Well, Jamila wonders whether this result is true at her large high school. Look at how that's worded. She wonders if it's true. She doesn't have a suspicion that it's lower than or higher than 85% at her school. She just wonders if it's different than. So she asks 100 students how much sleep they get. 75% reported getting less than the recommended amount of sleep. Okay, our task is to write the null and alternative hypotheses, and then I'm going to have to cram it in there. I'm going to have to define the parameter of interest. Well, the percent thing tells me we're talking about the proportion of teens, of all teens at her high school who get enough sleep on school nights. And the national study, the null always has an equal in it. The national study says that 85% of teens aren't getting enough sleep. So that's 0.85. P is always a decimal. Don't put 85. It's a decimal between 0 and 1. Well, she wonders at her school if it's 85% or something different. So what symbol should I use right here? Greater than, less than, or not equal to? Not equal to. 85%. That is a two-sided alternative hypothesis. The whole one-sided, two-sided thing only goes with the it only goes with the alternative. The null will always be equal to. Okay, all you need to do at this point is tell me, what does P stand for? And if you're kind of reading back up in the paragraph, it just represents the proportion of teens at her school. Specifically at her school. That's our population. Proportion of teens at her school who aren't getting enough sleep. And you can word that however you want. You can put too little sleep the same way it says it up in the paragraph. So you need to be very, very comfortable with writing your hypotheses. That's the very first thing you're going to have to do on your project. When we give you a problem, you've got to write your hypotheses. If you don't do that the right way, everything else falls apart. These next couple of bullet points aren't super duper important. I'm going to sail right through them. Kind of common sense. You should always state your hypothesis before you see the data. In science class, you're not going to do the experiment and then state your hypothesis. It's the same thing in statistics. State your hypothesis before you see the data. And then hypotheses refer to population, not a sample. That's just saying this. You're only going to ever see the symbols P or mu in a hypothesis. You're not ever going to see P hat or X bar in a hypothesis. Ever, ever, ever. If you've got a multiple choice question and you see P hat and X bar in a hypothesis, mark it out. We're always referring to population proportions and means. Okay. I told you hypotheses are important. What's even more important than that is something called a p-value. Today, I'm going to give you a p-value, and I'm going to say, what does it mean? Eventually in this chapter, you are going to calculate the p-value and then tell me what it means. So we're going to build up to that. It says, it may seem strange to state a null hypothesis and then try and find evidence against it. Kind of feels weird to do that, right? But think about innocent until proven guilty. What we're going to do is we're going to always assume that the null is true, but we're going to try and find convincing evidence for or against that. Don't read the gray box. It's really confusing. Let me show you what this whole p-value means. Here is a simulation of the free throws made out of 50. This is exactly what we did as a class, but instead of 19 little dots, there's 400 dots. It says right there. 400 dots. Each of these dots represents the proportion of shots made out of 50. If you want to know the p-value, then just circle what happened in his sample proportion was he made 64% of the shots, and you can see they've already kind of lightly circled. Circle everything that's 64% or smaller, so 64% or worse than that, and there are 3 dots. Out of 400, so the proportion of times that you get a result of 64% or worse is 0.0075. That's really small. That's only 0.75%. There's a very small chance that what happened to him, the 64%, very small chance that would just happen by chance alone, that he was just having a bad day. So everything boils down to this. You're always going to look at your p-value to draw conclusions. So this p-value stuff's really important. So here, what you would do is to interpret the p-value, you would say, all right, this only happened very, very little amount of time. So what that means is there is about a 0.0075 probability Here's what a p-value actually is, you guys. It's the probability of getting a sample proportion of 64% or less by chance alone. You're saying that there's only a 0.0075 probability that what happened to him in the sample would happen by chance alone. Think about what that means. We're gathering more and more evidence that this guy is exaggerating and he's really not an 80% shooter. Okay. Turn the page. This one's actually very easy. This should feel really smooth moving through this problem. Calcium is a vital nutrient for healthy bones and teeth. The NIH recommends a calcium intake of 1,300 milligrams per day for teenagers. So they say you should get 1,300 milligrams of calcium a day. Well, the NIH is concerned that teens aren't getting enough calcium. So if I made you write the hypotheses, you would have to infer, well, if you're not getting enough calcium, then we think that you're probably getting less than the recommended amount. So tell yourself that's where this less than symbol is coming from, because eventually you're going to have to write your own. The hypotheses aren't going to be given to you. You're going to have to write it yourself. So if you're reading in the paragraph, I don't think I'm getting enough calcium, you have to really stop and think, that means I think that we're getting less than what we need. Is this true? Researchers decide to perform a test of, here's your null and alternative hypotheses. Is this one or two-sided? One-sided. That's going to become really important in the chapter later on. It tells us that mu is the true mean daily calcium intake. I'm just going to highlight this because I'm going to copy this down in one of my answers in a second. We're talking about the average daily calcium intake of all teenagers. So they asked this random sample of 20 teens to record their food and drink consumption for a day. They compute the calcium intake, and then the data analysis reveals that X bar is 1,198 milligrams, standard deviation 411. Researchers perform a significance test. Here's really what you care about. The p-value is 0.1404. You don't really know what that means yet, but here's a p-value. A says explain what it would mean for the null hypothesis to be true. Now that one's really easy. Look at the null hypothesis, the top one, the HO. If this is true, then what that means is the average daily intake of calcium for teens is 1,300 milligrams. So if A is true, or if the null is true, then what that means is the true mean daily calcium intake, I'm copying from the paragraph, that's what mu means, for teens is 1,300 milligrams. That's the recommended amount. So if the null hypothesis is true, teens are getting enough calcium. B is a completely different question. It's saying now interpret the p-value that we got. When you get a p-value, again, eventually you'll be calculating that and then drawing a conclusion, but today I'm just giving it to you and saying, hey, interpret that. What does that mean? It means that there is about a 0.1404 probability which also is the same thing as saying a 14.04% chance. Sometimes our brains work better with the percentages. So either of those, you can write it either way, like in your project when I'm asking you to draw conclusions or whatever. You can write it either way. So there's about that much probability of getting Well, then you have to reference what happens in the sample. Okay, remember the free throw shooter? He shot 64% in front of us. So in this problem, we're referencing the sample mean, which is x bar, and that's what I'm going to write next. So there's only a 0.1404 probability of getting 1198 milligrams or less by chance alone. Of getting what happened in their sample by chance alone. Here's how I knew how to write that I was supposed to write the word less right there. Look at your symbol in your HA. It says less than. So if that had said greater than, I would say or more by chance alone. Just pausing to make sure you make that connection. Okay. Very last thing that I'm going to teach you is how to make a conclusion, how to draw a conclusion based on the p-value. Here it is in this box. This box is going to be so very important to you. You guys, I teach statistics and I always reference this little box to make sure that I'm not messing something up. If the p-value is small, you're going to write this. We reject HO. That's the wording you must use. We reject it. You can't say we hate it. You can't say it's not true. You have to say we reject HO. We reject the null. And the conclusion that we make is that there is convincing evidence for the alternative. Now that makes sense because if you say that the HO, if you reject the null, that means that you found convincing evidence for the other one. If the p-value is not small, here's what you must say. It's really strange. You must state it as we fail to reject HO. You guys, the same thing as failing to reject something is accepting it, but you're just not allowed to write it that way. You can't say we accept HO. You have to write it as we fail to reject it. Well, if you fail to reject the null, then the conclusion that you make is that there's not convincing evidence for the other one, the alternative. If you have no idea what's going on, just hang in there, okay? Because this is all very abstract until you start to work some problems. Notice how it says if the p-value is small or not small. What in the world is that? Well, our threshold is it's considered small if it's less than 0.05 or 5%. So now, today, when you're given a p-value, you decide first. Look at this box. Is it small or not small? And then from there, you decide, should I reject the null or fail to reject the null? And then from there, you decide there either is convincing evidence for HA or there's not convincing evidence for HA. It's kind of like a three-step process. There's a flow to it. One more thing, and I already said this a second ago, but you're never, ever, ever going to write, we accept HO. You just don't write it that way. Make sure in your project you don't word it that way. That's the same thing as saying we fail to reject. That's the same thing. Write it that way instead. So we're going to look at example 3. We're going to see what the p-value is. And from there, we're going to draw our conclusion. Here's that calcium problem again. Data analysis revealed all of this stuff, blah, blah, blah. The p-value is this in the calcium problem. Based on the hypotheses, basically at the top of your page. So again, the null is that we're getting 1,300, the recommended amount of calcium. The alternative is we're getting less than that. Based on this p-value, what conclusion would you make? First things first, is that p-value small or not small? It's not small. It's not 0.05 or less. So p-value is not small. So then there's the flow to it. Look in your box. If the p-value is not small, how do we word the next part? We fail to reject the null. Yes, fail to reject the null. The conclusion, what you actually need to write in sentence form, is there convincing evidence or not against the HA? So I'm looking back up here. Boom, there's not convincing evidence. Don't just write of HA. There is not convincing evidence of HA, comma, we need to write in context of like this calcium stuff. What does that mean? So there's not convincing evidence of this. Look what I'm pointing to. That teens are getting less than the daily recommended amount of calcium. And that's it. That teens are getting less than the daily recommended amount of calcium. Take your p-value. Is it small or not small? From there, tell me if we fail to reject or reject the HO. From there, tell me, does that mean that there is convincing evidence or not against HA? Okay, we're done with the notes.